So one of these functions is continuous and the other is not, although they look very similar. So some examples of being not continuous would be if, for example, there was an asymptote. So let's say this side goes up to infinity and this side goes down to negative infinity. That's not continuous. If there was some type of jump in the function, that's not continuous. And if there was some hole in the function, that's also not continuous. And so one of these has one of these problems and the other one does not. Well, if you look at both of them, at x equals 3, we've got division by 0. And so whoever created this, namely me, tried to remedy the problem by saying, well, when x does equal 3, don't use that over there, just say that the function is a 0. Is that good enough to fill in the problem? So really, if it was this, filling in one point is not going to plug this gap. It's not going to stop it from being not continuous. The same thing right here with this asymptote. You can't say, well, I'm going to fill in this big gap by putting in 1 point. But you can do that when there's this situation. So this is called a removable discontinuity, because if there was only that little hole in it, you could fill it in with one little dot, if that was its only problem, and then it would change from being not continuous to being continuous. So one of these has a removable discontinuity and the other does not. Well, we can, if you take a look at this, we could figure out more about this function by factoring. So f of x on the top can be factored as x minus 3 times x minus 3, since it's a positive 9 and then negative 6x. And once we've done that, then this factor of x minus 3 can be cancelled. And that act right there, that's the same thing as filling in that dot and making it continuous, because I've just removed the thing that was causing division by 0. And so basically it's a function that is a line x minus 3. So that has a slope of 1 and it goes through the y-axis at negative 3. And then a slope of 1 would mean that right here at 3 it also goes through, so that the slope would be 3 over 3, 3 over negative 3. Oh no, it's positive slope, so 3 over 3 is 1. But anyway, the question is, then this said, at x equals 3, fill in the hole that it's at a height of 0. And does that work with this information? When you substitute a 3, is it supposed to be 0? Because what I'm checking right now is that I don't have this situation. So originally I had a hole in the graph, and then I decide, okay, I'm going to fill in that hole. There you go, I filled it in. So I'm trying to make sure that where the hole in the graph was is the same as where it was filled in. So this says to fill it in at 0, which I did. This says if you're using this x minus 3 and you had x is a 3, then sure enough you would get 0. So it seems that it's a continuous function. It's not like that. So take a look at the graph of the original. So here's the original, x squared minus 6x plus 9 divided by x minus 3. And there's the original, and if you trace and plug in a 3, sure enough, there's a hole in the graph. And the hole is right here at a height of 0, and so this then fills in the hole, and it's continuous. So this one no longer has any holes or gaps. But if you take a look at this one, so this one can be factored as well. The bottom is x plus 3 and x minus 3. The top is x plus 3 and x plus 3. So we can do canceling, but the x minus 3 is still in the denominator, which means that it's still going to be undefined when you use x equals 3. And that means it's got an asymptote at x equals 3. We weren't able to remove that asymptote. And then to see what that one looks like, here's the second one. Sorry about the glare. And take a look at the graph, and you'll see that it's got an asymptote there at 3. This side goes down forever, and this side goes up forever, so it's not continuous.